Good morning, everyone, and welcome to the second day of the seminars of Assembly 2009 summer event. And the first guest today is Niko Suni, who has 20 years of experience of programming in general, and he is going to talk us for DirectX 11 today.
Thank you.
Please welcome Niko.
Thank you. So today we are going to talk about Direct3D 11, the new graphics application programming interface, which is available for Windows Vista as well as the 7 system. As Suni mentioned, my name is Niko Suni, and I am an independent consultant working from Lahti and working for international clients such as Microsoft and Sandvik and many others. So let's get started. How many of you has used Direct3D in the past? And those who haven't, do you know what DirectX and Direct3D is in general? Okay, so I assume that most of you have a general understanding of 3D graphics programming in general, and programming especially for Direct3D previous versions, such as 9 and 10. Because I will be talking about new features introduced in 11 specifically today. And the first, I should mention that you can interrupt me if you want during the session, if you don't want to ask the questions after the session. Please ask for microphones if needed. So first topic is programmable tessellation. So tessellation is the process of generating smaller geometric primitives from a higher order primitive, such as knobs, patch, or some other higher order primitive that can't be directly processed by the graphics hardware. The Compute Shader is an API that allows general programming on the GPU by using all its cores as needed. And it's very flexible. Multithreading has been refactored, so it allows fully multi-threaded resource creation, and also it allows you to record command lists so that you can play them back as display lists in OpenGL. But this has nothing to do with OpenGL per se. Shader Model 5 introduces a lot of new features. For example, the Compute Shader is part of that. Then there's two different shaders for tessellation control called Hull and Domain shaders, which you can control to use the tessellation. The precision sampling and rendering. There has been improvements in the requirements, such as bit depth precision when sampling from textures and stuff like that. And then there's programmable anti-aliasing. So you can query a lot of things about the geometry of a pixel on the pixel shader. Then there's a lot of other things which I will mention after the session. So Direct3D 11 works with Vista and 7 and the corresponding server systems. It will not be ported to XP, as wasn't 10 either, because the driver architecture is so much different. Hardware platforms. AMD has produced some cards, I know for a fact, and one of my colleagues has already the hardware, but they didn't get enough for me to get one. So we are going to run the reference rasterizer today. The warp is addition to the 3D pipeline, 3D driver system. It is a software driver, but it's optimized for speed, and it implements 10 and 10.1 feature levels. It doesn't need any graphics hardware, but it is about 10 times slower than a dedicated graphics card on 10 and 10.1. But if you're programming casual games, then it might be a good idea to use warp if you are targeting Vista 7 anyway. I'm going to talk about some specific techniques that are much easier, or at least possible, in 11, which are very cumbersome to do in older APIs. Insane geometric complexity means that we can take a very small amount of input geometry into the card and output millions of triangles by using formulas that we feed to the tessellator. And the tessellator doesn't have to store the generated stuff, so it's very fast. Photon mapping, we can use the Compute Shader to do some crazy stuff, like scatter some photons around and check where they hit and bounce them off geometry all inside the GPU, so we don't have to touch the calculations in between on the CPU. Motion blur with rotation and translation. Direct3D 11 introduces the concept of indexable resources. So we can, at shader runtime, we can address which slide of a texture or array we want to use and which pixel of the texture array we want to use by using integer registers. So this helps enormously in using texture arrays and volumes in general. Multi-threaded drawing enables us to use all the power of the CPUs in modern machines, because the common scenario is that either the GPU or CPU is idle while the other part is doing something. So multi-thread drawing enables us to tap into the power of the CPU in order to feed the GPU more efficiently. Abstract shaders. And I'm going to discuss in detail about this soon. Abstract shaders, we now have interfaces and base class support in HLSL shading language. So we can design an abstract shader that calls methods of an interface and supply the implementations of the interface during the host runtime. So we can dynamically assign shader logic after we have compiled and set the shaders. And it's very fast also. So here's some detailing. work that I have done. First, when I first touched Direct3D 11 last summer, I immediately thought about using as less geometry as possible to generate as much geometry as possible just for the sake of it, in order to see that it actually works. And it does. The input mesh is a collection of 4 vertices that form a solid, as you can see. And the output is n triangles, because the hardware can calculate the tessellation factors on the runtime based on the Hall shader. The tessellator works at the patch level, and the use of tessellation requires 2 user-defined shaders, the Hall and domain shader. The Hall shader has 2 distinct parts. First, it passes through the control points to the hardware tessellator, and it also calculates the tessellation factors, that it's how many geometric primitives do we want to subdivide the input primitive to, basically. It's very flexible because there's a choice of multiple tessellation partitions, such as integer partition, which divides the edges into integer divisions, so that they don't seam between each other so much or anything. And then there's a power of 2 partition, which reduces, for example, if you use displacement mapping on the results, then it generates seamless results also. And there are a couple of other partition methods. So the Hall shader works by first calculating the edge and inside tessellation factors. It passes them to the tessellator, and the Hall shader itself calculates possible new control points from the input control points, but it can also pass them through from the vertex shader if needed. Then the tessellator runs, and it generates new triangles or lines based on the instruction from the Hall shader. And it doesn't look at the control points at that point, but it just uses the edge tessellation and inside tessellation factors. Finally, after the tessellation hardware has done its job, it calls domain shader. And domain shader is called for each output points that the tessellator has generated. And that's where we calculate the new positions and attributes of the new vertices. So it's like a pixel shader for geometry. So the tessellator gives you a point and a parameter space UV coordinate on the triangle or the patch, the rectangular patch, or an isoline that you will then use to evaluate the surface. And I have a demo for this. But ironically, from the presentation title, New Avenues of Performance, the refast isn't that fast at all. So, because I don't have the Direct3D 11 hardware with me now. But the tessellation itself is a relatively fast operation anyway. So I put my Visual Studio on the second screen. Then I put the tessellation factor. This is a constant buffer which I bind to the shaders in order to control some of the parameters, in the shader. And the test quality factor is now 1.0. That means that it only generates one new triangle per input triangle. And I will show you soon how the shaders use that. This is just constant buffer updating. Let's hope it builds. Yeah. So now it went to this screen, but anyway, this is effectively the representation of the original input triangles. I didn't take the pixel shader away for the sake of demonstration now, but as you can see, it's very coarse. It only has 4 faces and 4 vertices. But I didn't design any UI for this demo, so I have to manually go to the source and update some stuff in the hardcore programming sense. So let's change this to 4. And now what we get is triangles that have been divided to 4 at each edge. And the domain shader also applies some logic to make it egg-shaped. Essentially, the hardware would generate new vertices on the fly based on the logic that the hull and domain shader define. And I show you a little bit about the hull and domain shader. So I put all my shaders of the egg in the same file. This would be a no-brainer if we use the effect framework, but as of now, the SDK doesn't support the effect framework. But on Direct3D 11, but the next SDK should be out soon, very soon, which does support effect framework on 11 plugins. So we don't have to do a lot of this stuff that this file does. Correction, what this file does. Most of this stuff is for initializing buffers and stuff, which the egg doesn't really have that much buffers, but anyway, there's a lot of work to initialize the shaders manually. But the egg shaders, there are some structures. So the vertex shader input is just a simple vertex which contains position. Vertex shader output is also equally simple, but it also includes a separate transformed position. the hull shader output is basically the same as vertex shader position because in this demo, I almost directly pass through the control points without modifying them in the hull shader. This is the constant data output structure that the tessellation engine requires. And it contains, depending on a triangle, whether you have a triangle or a rectangular patch or a line, it requires a certain amount of tessellation factors, which are floating point numbers. And it also requires an inside tessellation factor if you have anything but a line which you are going to tessellate. The constant buffer is just standard 3D stuff. The test quality is passed here. The vertex shader does almost nothing except transforms and passes through the input control points. Here is the interesting stuff. The edge constant function, which I've named egg const function, takes the input control points. It also, the hardware generates a patch ID based on the input geometry ID. And we can use that to determine which patch we are dealing with right now. This is the simplest case that we only assign a constant value to the tessellation factors. And then this code, I'm not going there right now, but then there's an intrinsic functions which allow you to both process the edge tessellation factors so that they are compatible with the current partitioning scheme, which is defined here on the hull shader core, and also to calculate the inside tessellation factors based on the edge tessellation factors so that we get even distribution of tessellation across the patch. So basically we just calculate the tessellation factors here in this edge constant function. Then the hull shader itself takes as an attribute the patch constant function. We could also calculate other stuff that remains constant across the patch in the patch constant function. The edge tessellation factors are just what the tessellation requires at minimum. It also defines what maximum is, so that it can hint the hardware how much internal memory it has to allocate to run this shader, if any. Output control points. So we basically tell the domain shader what to expect from us, and output topology can be triangle clockwise or counterclockwise or line, because the tessellation hardware only works on those primitives. Basically, the triangle variants are the same, but the normal is inverted, so that the order of the vertices is inverted. Partitioning, that I mentioned that a bit earlier. It controls the scheme in which the edges are tessellated. I use POV now. POV2 for powers of 2, so the tessellation factors are even, and raised to the powers of 2 so that at a given edge, all the tessellation factors are the same if the edge parameters are the same. And the domain is either triangle, line, or rectangle. Basically, the Hull shader core itself only passes through the input control points in this case, but we could do a lot of more complex logic, such as calculating the patch constants for a Bezier patch given triangle and its normals. This would be the place to do that. Then domain shader. In between here, between the Hull and domain shader, the tessellator is run, and it does the job of generating the new geometry. Then the domain shader evaluates the new positions of the new positions and other attributes of the new geometry given given the domain location, which is a barycentric coordinates over the patch if it's a triangle, and x and y parameters if it's a rectangle. For a line, it's 2 values. So the rest of this is just the egg logic. And the pixel shader is just standard pixel shader stuff which shades the egg, as you can see on the demo. And that's my mouse. Okay. So if we put this at 16, this doesn't have to be even constant because we calculate the real values in the Hull shader. But it's still fast on the refrest anyway, as compared to the usual refrest speed. It does rotate, but you might not see it very clearly because the rotation axis is straight up. And that's not the limit of what it can do. But let's move to the next topic.
One question.
Yeah?
What kind of shapes can you do with that? Just use basic mathematical shapes, or?
The question was what shapes you can do with that. We can do anything that we can feed to the shader system. So we can input a full polygonal mesh. This is an actual polygonal mesh in the case of egg 2, but we can also input Bezier control patches from, say, 3ds Max or something, and then use the Hull and domain shader to process them. So we don't have to store the fully tessellated geometry anywhere. We can just run them on the hardware. And we can dynamically allocate how much we want to tessellate, given normals and edge lengths, for example. So that's very flexible. This demo is simple because I don't have access to the hardware now, and I don't even have access to a fast machine now. So this is necessarily simple stuff. But I've seen the hardware work in action. It's very fast. Well, let's move to the next topic. I have to admit that I have some bugs, but I don't know. I'm almost sure that they are not my bugs per se, but some alignment issues on the shader compiler as of now. Because this I rendered with Jaffray, which is a ray tracing renderer, and it basically forms the lighting values of the images by scattering photon rays into the geometry and bouncing them back from other geometry a number of times, so that it accumulates the lighting values. And you can see slight bleeding of light here, so the light has bounced back off this face here to the floor. But it might not be as clear as I intended it to be, because the gamma values are different here than at my home working station. But basically, I tried to do the same on compute shaders, and for some reason it doesn't find the right geometry. We can pass the geometry as a buffer to all the shader stages, and we can also use a new feature called structured buffers, so that we can at the shader definition, we can mark a buffer so that it uses a certain structure of data. So we can use other stuff than float force or float ones or simple integer or simple vectors of anything. So we can now use actual arrays of custom data. And the result would be something like this if the photons were correctly in their places. But this is my results as of today's compiler. And I'm waiting for the new compiler so that I can test with whether it's my logic or theirs, which is wrong. I have a demo of this tool, but it's much slower than the egg demo, so I'll first go through it with you. So, in the hardcore style, I'll just change my demo contents, and this is all ordinary initialization stuff. I load the mesh from an object file that for which I stole the loading code from the DX SDK. But it's really easy for me when you're testing some stuff. It's just text, and you just pass it line by line in order to find the stuff. We compile the shaders. Compute shader is compiled in the exact same way as the other shaders. But it's used a little bit differently. You can also assign constant buffers and other textures and stuff to it, as just like you would do for a pixel shader or vertex shader. But the compute shader is a different animal from the rest of the shaders because it doesn't specifically process graphics. It can use all types of structured data and vectorized data and buffers, what you can use in the rest of the shaders. But as of Direct3D 11, you can also use structured buffers and read and write buffers. So you can basically handle the GPU memory as a heap of memory, which you do have to allocate from that heap manually in advance. But you can basically use random access operations on the shaders, both compute and pixel shaders on Shader Model 5 hardware. Shader Model 4 hardware also supports compute shaders, but it doesn't allow as much flexibility in writing the stuff out as the CS5. And there are some other smaller limitations. That's because of the way the hardware is implemented. We create a Photon map using an unordered access flag, which tells that we want to write also this resource in the shaders. And I'm using a R32 unsigned integer format because I want to use atomic operations that are available on the shaders now. So we can use deterministic non-locking logic to update values across multiple threads without fearing that they conflict during the point when the value is incremented or decremented or multiplied or whatever. We then create the textures as normal. We also create a shader resource view for the vertex buffer. This is made possible by the fact that we can now use structured data in the shaders. So we can input the vertex data structures directly in the shaders without using vertex shader to input them. Then we set the shaders, and Compute Shader is dispatched using a different method from draw, because it's really not a drawing operations that the Compute Shader necessarily does. So there's a separate method for dispatch which takes thread group counts. How many groups of threads do we want to assign to this task that the current Compute Shader runs? And then the hardware, upon calling this, it begins to do the job that the Compute Shader defines. And the Compute Shader itself can be very, this is the bulk of the code which has the bulk above. Well, this is a minimal Compute Shader. It only requires a single function, and even this is not actually necessary, but it is good to have the thread ID available on the Compute Shader so that you can parallelize your calculations somehow. You can differentiate between different threads. And there's also a group ID available and a lot of other stuff. Here you can see how we can directly write to a resource. Now, Photon map RV is a read and write resource, which is a type of RV texture 2D and unsigned integer contains. This is really easy to use per se, but here is a structured buffer, and I don't think that the actual structures need to be aligned in the final version, but I did this to eliminate some bugs, so I aligned it to 16 bytes because the shader registers are aligned on 16 byte boundaries. So I thought that I could fix the bug that shows up in the demo. Let's run this. That's just ordinary ray tracing logic, basically, what a real compute shader does. And you can come talk to me after the session if you want to hear more. I don't have time to discuss all the details here. This is really slow. I try to move the window. This is slow not because we use the compute shaders themselves, but for the fact that the compute shaders calculate millions of calculations in order to do the ray tracing. And real hardware, I have heard that it would be on the order of 2,000 times faster than the current RefRast, given a standard PC CPU. Now I did draw something, but since I moved the window, it erased it also. Let's wait for a little bit more. Well, basically the bug is that the ray tracing logic doesn't return the right triangle in which the rays hit. So it results in rays being cast to the wrong faces. The ray tracer evaluates the UV of the triangle that the ray has hit, and from that UV it calculates where in the light map the current point is, and directly adds the photon value into that point. It's all that simple. And this has the advantage that we can use sparser logic than what the light map resolution actually is. Let's move on. I don't have a lot of time. Okay. So I'm going to skip motion blur. Essentially, you would use texture arrays and correct indexing in order to sample from multiple textures and at the same time, and also render to them via a single draw call. That's the magic of this. Multi-threaded rendering, I talked about a little. So the APS refactored so that resources can be generated on other threads than the rendering thread. Abstract shaders, we can define HLSL interfaces and base classes, and we can assign the class implementations at runtime. Not at the shader runtime, because the shader runtime doesn't have linking capability. But from the CPU side, we can assign implementations to the shader classes. And that's very fast, even on RefRast. But I don't have a demo for that. There's some stuff. I can talk about this with you outside the seminar room if you're interested. most of the new stuff is performance enhancements, so that you can more directly do the stuff that you were able to do before, but it was bad performance because you didn't have a direct hardware layer for that. But the compute shaders, they are entirely new stuff. There has been stuff like GPU before, but now this is the first time that there's a unified interface across all hardware manufacturers to use general purpose computing. And it also works on slightly lower level hardware than 3D11. Since 7 was released yesterday on MSDN and TechNet, also Direct3D 11 runtime was released yesterday, basically. But the SDK hasn't been updated just yet. I'm expecting that it will be this week or the next week. So we have the effect framework again, and also they should have corrected most of the compiler bugs by then. We can talk about this outside the seminar room if you want. Direct3D and Direct3D. I'm on the bonus content in case we have time. But please come talk to me if you want, and send me email if you want. And I will be available here after this session also. And I will publish the demos as when I get bugs fixed. But I don't know the form in which I will publish them. It might be an online book or gamedev.net or some other form. But they will be on the net. And here's some links. If you are not familiar with gamedev.net, it's an active community of game developers, and the DirectX community in particular is very active in there. So I recommend visiting us there if you want to learn about Direct3D in practical usage, as well as to ask for help in implementing something. So we are out of time now, so I will thank you, and please come see me at the seminar if you want.
Any questions? I think we have time for one, or... Okay, you can continue later. Thank you.
Thank you.